So the next part is about the breadth first search BFS algorithm. So this is the one of the code for the BFS. As you know already from the pseudocode, we want to start from the graph and then we start from the S, a particular node in the graph. And then all the nodes are undiscovered. This is the code that you already saw in the pseudocode. And then this is the first part. So we want to make all the nodes and all the vertex undiscovered. So after we have this BFS complete, we will do this BFS G, S until all level. So we have the level. This is the first level. This is only S. And then the next level, we will go until the length of the level is not greater than 0. Okay, so we already learned this one. Now I'm going to use the graph Korea. I would like to check the BFS from the graph Korea. So with this incoming, I would like to check from the incoming part. Okay, I guess the result is similar with the DFS. We have from Busan to Daejeon, Daejeon to Suwon, Suwon to Seoul to Gwangju. Okay, the result of BFS is similar. And then for the graph one, yeah, you can check later with the DFS. I guess it is also similar. And the graph 2, yeah, is almost similar. Okay? Because those two, BFS and DFS, if the graph is all are connected, okay, it is almost similar. Yeah, this is the example. I'm just using a very small number of data. Let's say in this example, I use only 5 nodes. And in this example, I use 1, 2, 3, 4, 5, 6, 7. I only have 7 nodes. Okay. And in this, yeah, I have only 1, 2, 3, 4, 5, 6, 7. I have 7 nodes. But in your team project, I ask you to create many nodes later in order to check the runtime performance. I have not checked your video, but yeah, I just got an email from one team. If you have not submitted your YouTube link, please submit to the e-class, because I will check that submission to the class and then. Okay, Chewante, yeah, I got your message. So if I think Crimson Tech, I just saw your email. So please submit your file and also your link to the e-class. So I want to make the progress evaluation for public. It means you can see what your friend, what other teams works. Okay? So you can have some kind of motivation how to improve your team project. Okay? Okay, so you can have the Pyongkat. Okay? So you can check what other teams do until now. So you can have some motivation what you can do next until the final presentation. Okay. Our final presentation will be maybe about, I don't know, 10. So I will check the schedule again. Okay, so on Monday, I will let you know when is our final presentation. Probably it is 10 or 17, I'm not sure. Last time, did I mention to you? I think no. Okay, so I will inform you on Monday. I will check this on your video. Okay. So it is not mandatory. Okay. So this Pyongka, what is the meaning? This one here, Sangho Pyongka. It is not mandatory. Okay. 원 하시는 학생은 하세요. If you do not want, no problem. Okay. But if you want, you can see what others do. Okay. So I will be objective. I will give the evaluation objective. If you are good, of course, I will make a good point. If your result is, your progress is still low, then I will also give you a low point for the progress evaluation. Okay. And when you are doing this experiment, okay, as you know, if only 10 nodes or if only 5 nodes, it is too small. You cannot run the time performance. So you need to have more nodes. How you can generate more nodes? So I would like to teach you how to create the graph randomly. Maybe you will say, oh, is it reliable to have this random graph? In terms of the performance, no problem. But in terms of the result, for example, I want to find the shortest path. If you use the random graph, of course, the shortest path will not be suitable. So this graph random generator, it is only to check the time performance. Now, I would like to use this network. There is one library in Python, we call it network X. And in the network X, I would like to generate the random graph. This is the function GNM random graph. And let's suppose I want to create 10 nodes and I want to create 30 edges. Then I can create the GNM random graph n, m. So I will do the iteration for all the edges, and for every edge which is in the g.edges, yeah, we will write it into the f. So if I run this, yeah, it will create 10 nodes and 30 edges. Yeah, you can see there is one file here. It will create the test.hrlist. This one. So it can generate a function. So this function will create the G1 0,8, G1 0,5, G1 0,7, and so on. So it creates a new edge and it is random. If you want to use this file, yeah, you can open the file and then you can do more things. Maybe you want to put some element, the mileage in random as well. You can also do that one. Now let's suppose I want to make it as a list. So this is the same way to generate the random graph, and then I want to make all the nodes into a list LL. This LL is a list and I want to make it as a tuple. Okay. in the tuple, you cannot change, you cannot modify the element. So that's why it is good if you use the tuple. And this is random. This is the 10 nodes and 30 edges. And after I have this tuple, as you know, in our previous part, the graph from the edge list is using tuple. So I can fit this tuple into this graph from edge list. And then this is a directed graph. Okay, if you want to say this is directed graph, then you can put as true. And this is the graph random 01. Okay. You know how to get the runtime. We learned from the chapter 3, we can calculate the runtime performance. Okay. So the function here is the function for your algorithm. Maybe you run the DFS, you run the Dijkstra later, you can put here. And then you can calculate the starting time and the ending time. And then we want to check what is the elapse. Now I would like to make the second random graph. N equals to 100, M equals to 300. So I will do this one. This is 100 and 300. And then I want to make another random graph, 1000 and 3000. Where is, oh, okay. This is the time performance. Okay. This is the time performance if I want to run with the DFS. And Fn is the function. Fn is the function. Let's say, sorry, Fn is the graph that you want to run using the DFS. So I want to check the runtime performance of 5 data. Maybe the first is graph Korea, and then I create the random generator graph, random 01, random 02, random 03, random 04. So I can run T1 is this one, T2 is random 01, T3 is random 03, and T4 is random T4 is random 03. So if I want to check what is the T4, okay, it is 0.0029. It's still very low. Okay. Then you can create more nodes, create more edges. So you can see later what is the runtime performance. So let's say this is the 10,000 nodes and 30,000 edges. And if I check the T5, okay, 0.03. Then I can make a list. Okay, you know the list. Let's say here is the list of time performance of the DFS algorithm. Then I will make the T1 into the test DFS, T2, T3, T4, T5. And then I want to compare with DFS. So I again do the runtime. After I get this one, if you want to make with different function name, also it's also fine. Now I make with the same function name runtime, but here I use BFS. So I'm expecting when you are writing your report, if you use the Jupyter Lab later, please make some explanation. Okay, what is the meaning by your code? And now I'm using S1, S2, S3, S4, S5 for the runtime for the BFS algorithm. And the result will be added into the list BFS. And after getting the runtime for both DFS and BFS, we can plot. Okay? We can plot these algorithms. And I know that the X, maybe I can say this is the number of data. The first data, we have only 5 nodes. The second random, the random 01 has 10 nodes. Random 02 has 100 nodes. Random 03 has 1000 nodes. And random 04 has 10,000 nodes. So let's make an X to plot in the X axis. And then, okay, let's check first what is the result in the test DFS. Okay, this is the time performance of the DFS. And you can just make a very simple plot. Okay? You don't need to put a very complex plot for this one. Just want to see the plot in the term of line plot like this. You can use matplotlib. Matplotlib is one of the library in Python, and you can use it for the plot. And for this one, I use the matplotlib.pyplot, and I will use it as the PLT. PLT is the shortest of this function. And then I would like to import pylab. It is only to show the label. Okay, so I will put the label as a data, and then I will put the label as the time for the Y. And this is the DFS. And then the plot will be using the X, which is the data. And then the result of the test DFS will be plotted. And for example, I will use red color. Then this is the time performance of DFS. And if you want to compare with the BFS, then you can put 2 information. The first is putting the label, the X label and the Y label. And then we want to put the title DFS versus BFS. Let's make the first, the test DFS with the red color and the other plot with the blue color. And then we want to put the legend. The legend means this one. There are 2 lines, which is DFS and BFS, and we want to put it in the upper left. And at the end, we want to show. Okay, so this is the result. And yeah, in conclusion, the time performance of BFS, okay, yeah, when you do like this runtime performance, because I just do one time, it is good if you can do several times to check, because sometimes it will be different. It depends about the computer performance. If you are running a lot of software, if you're running a lot of programs, it will make your computation slower. Okay, this one is a little bit slower for the BFS. Yeah, it is different with the analysis here. So, and then you need to mention what kind of device do you use. Different device will give you different result. Okay. So I'm saying like this one, I'm using the laptop for doing this experiment. So when I use desktop, of course, the result will be different. Okay. And it is common when you are writing a scientific paper, they will ask you, what is your computer spec? The higher spec, of course, it will give you a very good time performance. Okay, so until the final presentation, I hope that you can show something like this one. When you have 4 algorithms, so it means you will show the time performance of 4 algorithms. And you will show like this kind of graph. If your data is too small, no problem. You can use only just to show that your algorithm works. So I can say that with small data, prove your algorithm in terms of applicability. So I want to know whether it is applicable or not. With big data, and you can use random at this moment, prove or just show the time performance of your algorithm. So your algorithm, yeah, it can be the shortest path or something related to your problem. And when you create your algorithm, make sure that you put it into one function. Okay. So like this one, it is in one function, BFS complete. Because when you have this one function, it will be easier for you to compute the time performance. Okay. That's about the graph. Any questions? Okay, if there is no question, then I will continue to the next chapter, which is about the shortest path. In this PowerPoint, we will learn 3 algorithms for the shortest path. Before I go to the shortest path algorithms, let's discuss about weighted graph. What is the meaning by weighted graph? And then there are some shortest path algorithm and some examples. What is weighted graph? We know already graph, and the weighted graph is something related with the elements in the edge. What is element? If you check on the previous example, we have the mileage. That's what we call as the weighted. In a weighted graph, each S has an associated numerical value. And we call this is the weight of the edge. Edge weights may represent distance, cost, and so on. So in this case, the flight route graph, we have this one. The weight of an edge represents the distance in miles between the endpoints airport. We call this is a weighted graph. Shortest path problem is a problem when you have a weighted graph and I have 2 vertices, U and V. We want to find a path of minimum total weight. So this is the key point. Minimum total weight between U and V. Length of a path is the sum of the width of its edges. Sum. So it means you will add all the numbers for every edge. For example, I want to find the shortest path between Providence and Honolulu. This is Providence and this is Honolulu. Then if you think that, okay, this is the shortest one, then you will add this number plus this number plus this number. some application that we already know in the graph. There can be a lot of applications. So it's also some of them like the internet packet routing or the flight reservation and driving direction, navigation. There are some properties for the shortest path. The property one mentioned that a subpath of shortest path is itself a shortest path. Subpath. So we know set and we have subset. It is also the same. We have path and we have subpath. Okay, subpath it means the sub element of one particular path. Property 2. There is a tree of shortest paths from a start vertex to all other vertices. We call it tree. So for example, if there is a tree of shortest path from Providence, we want to have a path from Providence. So if we want to have the shortest path to San Francisco, then there will be a tree from Providence to San Francisco. There are several algorithms in the shortest path. Now I'm just giving you the basic algorithm, the most common algorithms in this domain. Of course, when you are doing more study, if you want to enter the graduate school, you will have many more algorithms for the shortest path. So this one is only just the basic one, Dijkstra algorithm. It is the shortest path from one node to all nodes. And we will learn Bellman-Ford, which is the shortest path from one node to all nodes and the negative edges alone. Negative edges means the negative weight. And we have the Floyd-Warshall. So Floyd-Warshall is the shortest path between all pairs of vertices and negative edges allowed. Actually, there is one more. We call it DAG. So yeah, we will check all those algorithms. Dijkstra algorithm. In Dijkstra algorithm, we want to find the distance of a vertex V from a vertex S, and we want to find the shortest path. The shortest path means there will be no other path where the width is the most minimum. Dijkstra algorithm computes the distance of all the vertices from a given start vertex S. There are some assumptions for the Dijkstra algorithm. The graph is connected, so all the nodes should be connected, and the edges are undirected. So it is not for directed graph. And also the edge widths are non-negative. Non-negative means it should be positive. Okay. We grow a cloud of vertices. We call it a cloud because we will save all the vertices into one repository before we select it. We grow a cloud of vertices beginning with S and eventually covering all the vertices. And we start with its vertex V, a label dV. So later we will see dV. It represents the distance from S to V in the subgraph consisting of the cloud and its adjacent vertices. So later you will see the dV. It is the distance of P from a particular node. Let's say if it is from S, then it is from S to V. For every step, we will add to the cloud the vertex U outside the cloud with the smallest distance du. And we update the labels of the vertex adjacent to U. Maybe we will see example. Before I go to the example of the Dijkstra, in Dijkstra we will see some kind of edge relaxation. Edge relaxation means let's consider an edge E, U, Z, such that U is the vertex most recently added to the cloud and Z is not in the cloud. So now I know that my algorithm works from S to U and the distance from S to U is 50. U has been in the cloud. So we call this is the cloud. Okay. S and the other node here and U has been in the cloud. But Z is still not in the cloud. So the relaxation of HE updates the distance dz. The current dz is 75. How we can get this 75? We can get from the S, maybe from this to this one is 75. But if we look at this node, the current distance U, it is 50 from S. And then this current S shows that 10. It means 50 plus 10, it is 60. However, we have the distance Z is 75. So it means there might be another edges from this graph that can go to Z and the distance is 75. The edge relaxation means we want to update it by finding the minimum. The dz is the minimum of the dz. Dz is the current value compared to the du plus the weight e. Because there can be a path from u to z via the he. So I want to know the distance du plus weight e and then compare to the dz. Dz is 75. 75 compared to the du plus weight e, it is 60. So the minimum is 60. So we will not use this one, and the new dz will be 60 because it is the minimum. That's the way to find the minimum shortest path using the Dijkstra algorithm. Now let's see the whole picture, how the edge relaxation works. We want to start from A, and let's say we have this kind of graph. A to B is 8, A to C is 2, and A to D is 4. This is the width, or maybe this is the distance, or this is the cost. So using this information, I can just say that now the dz is the distance from A which is the starting point, A to A is 0. A to B, it becomes 8 because I know the distance is 8. So I put 8 here. What about A to C? The distance is 2. So I put 2 here to represent the dz. What about D? I have the 4, so I put this as 4. What about E? Because there is no direct edge, so let's just make it as infinite at this moment. So this is the first step. From this one, I can go to the next possible node for the shortest path. What is the shortest one? We have 8, 2, and 4. So the shortest one will be this C. So I will select the next node is C. After I select C, now they are on the cloud. Because A and C are on the cloud. Now I will update. How can I update? I need to update the incident edges of C. C to B, what happened? 2 plus 7. Okay. So it means we can update it into 9, but we want to find the minimum. What is the minimum between 9 and 8? The minimum is 8. Then we will still keep this one. Okay. What about C? Of course, yeah, this one is still the minimum. What about D? In D, originally we have 4. Okay. But if we go through C, we have 2, for A to C, and then from C to D, we have 1. Then we have the total 3. So what is the minimum? Between 4 and 3? 3 is the minimum. Okay. And then we have new value for E and F. For E and F, we can check if we want to go from A to E. So we have 2 plus 3. Yeah, there's a possible value, which is 5. From A to F, there's a possible value, which is 2 plus 9, which is 11. So we put this is 11, and then we put this one 5. Among those, so we have the C, D, F, E, and we can check the minimum, the next minimum after C is D, because it is now 3. Then we will go to D. We put the A, C, and D into the cloud. Now we will update again. How to update it? If we have the A to C is 2, and then A to D, we have 3, not 4, because the shortest path is 3. We can go from A to C to D. Okay. Now, what about F and E? If we go to D, yeah, it seems there is no update for E. But what about F? 2 plus 1, it is 3. 3 plus 5, Now it becomes 8. Okay. What is the minimum between 11 and 8? Of course, 8 is the minimum. Then we will update the f with the new value 8 later on, and the e is still the same, which is 5. And what about b? Yeah, b is still between the 8 and a to c, and b it is 9. Okay, so we still keep the 8. Now we select the minimum, which is E. So we go to E, and E is selected as the clock. We have the A, C, E, D. Now we are going to update again. The updated version will be, if we want to visit B from this path, so 2, 3, and 2. So we have a new value, which is 7. What about the other? It seems there is no updated. So the remaining will be still the same value. E is 5 and F is 8. Then we will go to the next lowest one. We already visited A, we already visited C, D, and E. So the next will be B. So we go to B. And B is 7 based on the new edge relaxation. And then the last one, we will check F. If there is no update, then F is 8. Then for this one, we will have this distance. From A to B, the shortest path is 7. And the yellow color shows the path. If I want to go to C, the distance is 2. If I want to go to D, the distance is 3. If I want to go to E, the distance is 5 with this path. If I want to go to F, this is the shortest path. Okay. This is the Dijkstra algorithm. And this Dijkstra algorithm, it is still using the graph G, and we want to start from S. So the idea of the relaxation is given by the condition. If the du plus the weight of u comma v is less than the dv, then we will add the du plus v, the w u comma v into the new dv, and then change to dv the key of vertex in Q. And this will be done for every vertex that is adjacent to Q. The Dijkstra algorithms, it is a graph operation, and then the label operation. So we find all the incident edges once for every vertex. And then the label operations, we set or get the distance and locate the label of vertex Z. Possible performance or the worst case performance will be the degree of Z. And if we want to set a label, it is only O1, so only one time operation. We can apply a priority queue. The priority queue means we want to find the minimum every time when we calculate the distance, and then we will remove the minimum. So you can use the priority queue, and each vertex is inserted once into and removed once from the priority queue. where its insertion or removal takes O log n. O log n means we can say like half. Okay, we will not check for all the possible nodes, but we just check for all the incident nodes. The key of vertex in the priority queue is modified at most the degree W times. So the degree W means, yeah, it depends on the vertex. So if it is all connected, maybe it will be longer. But if it is not all connected, then the worst case will be log n, where each key change takes O log n times. So the total, the Dijkstra algorithm will run O n plus m. N, it means the number of vertex. M is the number of edges. And we add with the log n time, provided the graph is represented by the adjacency list or map structure. And recall that the number of degree, if we do the summation, it will be 2 multiplied by m. Or the running time can also be expressed as this one, O m log n, since the graph is connected. So if n plus m, yeah, this is regarded with all the possible n and m. But if we are just having this property, degree v equals to 2m, we can also say like this one. Okay, this is the shortest path length algorithm code with the priority queue. We use the priority queue to adopt or when to remove the minimum key when we can find the minimum from all the paths that we calculated. Oh, okay. I guess that's all for today. I will continue the next one on Monday. Okay. Any questions?